traffic, clouds and precipitation, as well as the advantage in high altitude observational site is that you can get to study. So it's like a natural laboratory for understanding aerosol cloud interactions. So in plain lands, you will see clouds are at 3 kilometer, and we observe aerosols, and we don't able to address the cloud aerosol interactions. So IITM did some aircraft experiments and to understand this cloud aerosol interactions, whereas the aircrafts have several limitations. So we cannot fly whenever we want. We can fly only a limited period. So then, alternately, this idea was conceived to establish a high altitude cloud physics lab, so that we can address the cloud aerosol interactions for long term and understand the processes. In aircraft, we cannot have all the measurements. So we can have, because there are weight limitations. So we cannot have all the measurements. So in turn, ground-based measurements can give you opportunity to make all chemistry, all other information. So this is mainly I'll be talking on. I'll be talking on this high altitude cloud physics laboratory. So we also establishing UAV. In UAV, we are integrating the aerosol instruments, radiation instruments, so that we can probe the lower atmosphere. The LARS is lower atmospheric research using unmanned aerial systems, and see, all these processes may not be true what we observe in orographic regions. So in plain lands, there could be different processes which are not influenced by orography. So that's why we are also setting up a research test bed in core monsoon zone, central India. It's close to Bhopal. So wherein large number of lows and depressions pass through whatever forms in Bay of Bengal. It goes all the way to central India and give heavy precipitation. So extreme rain events. So to address that, we are doing this core monsoon test bed. And we also have a group works on radars. So they are setting up a urban radar network in Mumbai metropolitan region. That's a first test bed in metropolitan city. Then it will be extended to other metropolitan cities. Now I'll come back to my title of my talk. You all may be familiar. The aerosol cloud interaction is, represented in two effects, which is first indirect effect. First of all, aerosols directly influences the radiation budget through scattering and absorption. So indirectly, it can also influence the cloud microphysical properties. So it can enhance the cloud albedo. And the second effect is the cloud lifetime effect. When there are more aerosols, there will be smaller droplets. If there are smaller droplets, then it suppresses the collision coalescence efficiency and delays the warm rain process. So this is a schematic illustration that you can see for the same volume. If you have more number of small droplets, so then you can see the enhanced reflectivity of the cloud. So this is also called the Tommy effect or cloud albedo effect. So if the drops are small, you can see here the small droplets follow the airflow streamlines. In turn, it bypasses the falling larger drop. So whereas the large drops, you can see it collides with the falling drop. So in turn, the collision coalescence efficiency will be better. So if there are more aerosols, there will be smaller droplets, which suppresses the collision coalescence efficiency and suppresses the warm rain initiation. So here you can see the anthropogenic emissions, which gives rise to large number of aerosols. So then these aerosols, the direct effect is scattering and absorption. In turn, it influences the radiation budget. Indirectly, these aerosols act as a CCN or ice nuclei. So in turn, it enhances the reflectivity of cloud and cloud lifetime, and in turn, if the absorbing aerosols are there, it can heat the atmosphere. So in turn, the stability can get altered. If stability is altered, so you will see the other effects, thermodynamics and dynamical effects. And so in turn, the aerosols affect the climate through direct and indirect effects. So we need to understand these cloud active aerosols. So all aerosols are not cloud active. Some portion of aerosols could act as a cloud condensation nuclei. Very small fraction of aerosols can act as a ice nuclei. So to improve our understanding on aerosol cloud precipitation interactions, so we need to enhance our understanding on CCN and ice nuclei activation processes, and so in turn, like what physical and chemical characteristics control the activation of aerosol to CCN or ice nuclei. So this is the high altitude cloud physics laboratory at Mahabaleshwar. So Munnar is close to 10 degree north, I guess 9 degree or 10 degree north. We are at 17 degrees north. The Western Ghats goes all the way up to, from Kerala to Maharashtra, and so we are sitting in Maharashtra. Okay. So you are welcome to visit the lab. So whenever you find time, so the lab is always open to receive you all. So these are the research topics we address in high altitude cloud physics lab. So we make measurements of cloud microphysics, liquid water content, cloud droplet number concentration, cloud droplet size distribution, and in turn how these clouds are interacting with the aerosols. And if you know aerosol, whether we are able to predict the CCN, what is the aerosol cloud droplet number concentration, closure, and the cloud vertical structure and morphology using radars, and orographic cloud and precipitation processes. And what is the role of aerosol hygroscopicity? Hygroscopicity is nothing but the ability of water uptake of particles. And role of secondary aerosol in CCN activation, and role of volatile organic compounds in secondary organic aerosols, because as you all know, the Western Ghats is densely vegetated region. So the vegetation also puts out volatile organic compounds into the atmosphere. So with oxidation, see these VOCs also can get converted into particle phase. So this is a gas to particle conversion process. So in turn, this it can contribute to cloud condensation nuclei. So just to give a, so we are here in Munnar, somewhere 10 degree north, and our observatory is somewhere about close to 18 degrees north. And the objectives of this laboratory is to make long-term measurements and improve or develop the cloud condensation nuclei or ice nuclei parameterization, and what is the role of biogenic volatile organic compounds on secondary organic aerosols and in turn CCN activity. And you all know that so Western Ghats is a highly precipitating region. So Mahabaleshwar receives annually about 6 meters of rainfall. I hope Munnar also could be similar. The annual total, yearly almost 6 meters of rainfall it gets. So these are the experimental facilities available at Mahabaleshwar lab. For aerosols we have SMPS for particle size distribution, CCN counter, scattering and absorption measurements like nephelometer, ethylometer, and sun stereodiometer, and aerosol chemical speciation monitor, and recently we also put mass spectrometer. For cloud we have a cloud combination probe and the radiometric profiler to get the integrated water vapor and integrated liquid, and whole scale imager to continuously record the cloud fraction and cloud types, and ice nuclei counter and cloud radar, which is K band. And for precipitation we have several distrometers, impact and optical and video distrometers, and micro rain radar. precipitation radar, which is X-band radar. Additionally, we also have for chemistry, pulse IC and HDMA for hygroscopic tandem differential mobility analyzer. So with that we can get the growth factor and in turn hygroscopicity. And PTRMS is for VOC measurements. So these are the suite of instruments which you will get to see when you visit the lab. And so what are CCN? Variable subset of aerosol particles. So depending on its size and chemical composition and its water uptake ability, it can act as a cloud condensation nuclei. So this is a Kohler curve, and you can see the competition between the curvature and the solute effect will determine the activation of aerosol into cloud droplet. And there are studies which said that size matters most as compared to chemical composition. Dusek, he was showing that when the temporal variation of chemical effects on CCN activation is neglected, variation in size distribution alone can explain about 84 to 96% of variation in CCN concentration. But Hudson showed that this large variation in solubility parameter, and hence he says particle composition is also very essential. So there are studies showing size is important than the chemistry, but the chemistry also makes equally important. So these are some typical CCN supersaturation spectra observed at different places. You can see how it varies with the supersaturation. So CCN activation depends both on particle size and chemical composition. Again, if you look at the diurnal variation, the different types of diurnal variation you will see in different regions. So in our region, so you can see this is the top panel is JJA, which is monsoon. The middle one is DJF winter, and pre-monsoon March, April, May. So in all these cases, the right panel shows aerosol concentration and the left column shows CCN concentration. And you can see different type of diurnal variation. In monsoon, you will see a huge peak in the morning as compared to afternoon. Whereas in winter, you will see both morning and evening, you have similar type of peaks. In pre-monsoon, you have a higher peak in the afternoon. So it depends on different sources which is available in that region. So these are a summary of the different CCN measurements are ongoing at different places over India, covering from Uttarakhand, high altitude site. All are almost high altitude sites. Nainital, Darjeeling, Ponmudi. So these are the variability of CCN and the activation fraction. So activation fraction is nothing but the ratio of CCN to aerosols. If all aerosols can activate as CCN, then activation fraction is 1. If it is 0.5, you mean 50% of the aerosols get activated as CCN. And there are different measurements are going on over Indian region, which shows how this CCN is varying over different regions and spatially and temporally. So we also see different type of interseasonal variability. So this shows the diurnal variation in different regions. So this Uttarakhand, you can see a different diurnal variation. Mahabaleshwar, you have a different diurnal variation. In Kanpur, you have a different diurnal variation. So it depends on the sources prevalent in those regions. So IITM also has an observatory in the rain shadow region in Solapur. So they also make measurements there. And this is the CCN activation fraction in different regions. So what I'm showing here is the Mahabaleshwar and Tumba and Ponmudi, where IAST makes measurements. So there are some reports available for Kanpur also. So in turn, we get to see different type of variability spatially and temporally. So then we try to also see how the closure can be seen for a given aerosol observations. So whether are we able to predict the CCN quantity. So we looked at, so initially we were not having the hygroscopicity information. So only using bulk chemical composition with the aerosol chemical speciation monitor, you can only get the bulk chemistry. You cannot get the size resolved chemistry. With bulk chemistry, we try to estimate the mean value of hygroscopicity and try to see different combinations with only inorganic species and all inorganics and water soluble species. So with the different combinations. So when we included the all inorganics and oxygenated organics, so we were able to better estimate the CCM. So this is the result from Mahabaleshwar Observatory, and I think Sachin compiled all these chemistry measurements over different regions. So I think this can get us some idea how the CCN activation fraction varies in different regions, how the chemistry plays a role in CCN activation, etc. So this is the annual variability. So we have a long-term measurements. So this shows about 1 year of measurements. So clearly the top panel shows the organics and the bottom panel shows the inorganics. So you can see clearly in summer you have higher mass concentration of organics and inorganics, and whereas in monsoon you have less, and the other winter and summer we have a high mass concentration. Again, this is to look at how the new particle formation also can play a role in diurnal variation of CCN. So you can see this is one such event. So Vijay looked at several events on new particle formation. So this is one such event at how the diurnal variation of CCN can get impacted through NPF formation events. So to understand the CCN activation, so we need to have information on dry size of the particle, chemical composition, and hygroscopicity or water uptake. For ice nuclei activation, so we need to have the temperature and aerosol concentration and type. So this is one such a recent publication from our group. Abhishek Ray is one of my PhD students. He did this work. He looked at, first time he reported size segregated seasonal variation of hygroscopicity, and he also looked at, so there is a reverse trend of hygroscopicity versus size in Eichen and accumulation mode size ranges. So he also tried to develop a parameterization of hygroscopicity as a function of particle size. So he tried to see the closure. So I'll show some of the results. So this is the HTMA setup at our lab. So we have two DMAs, and you select the size and give it to the humidification chamber and see the growth factor, and from the growth factor you estimate the hygroscopicity parameter. So this is how there are two seasons, March, April, May, and winter. He looked at what is the size dependence of hygroscopicity and how it gets modified, how we can explain with the detailed aerosol chemical composition, size resolved aerosol chemical composition. So what you see here is for different sizes, you have size resolved chemistry, and with the size resolved chemistry, so how we can explain this, the observed growth factor and in turn hygroscopicity. And he also tried to look at the hygroscopicity closure, directly derived from growth factor measurements and indirectly derived through chemistry. Even in chemistry you have internal mixing or external mixing, and try to estimate the hygroscopicity through different methods and try to see how closure it is as compared to direct measurements of hygroscopicity. Parametrization, he tried to developed, so which fairly compared well. So he tried to put for different seasons how it works. So now I'll come to the ice nuclei part. I think Dr. Shweta will talk more on ice nuclei, so I'll just give some glimpses on ice nuclei. See, the formation of ice in clouds is very important, as ice formation is one of the key processes initiating precipitation. So it's a very small subset of aerosols as compared to CCN. So here is, say, 1 in million of aerosol particles get activated as ice nuclei. So we used a continuous flow diffusion chamber for online measurements of ice nucleating particles. Generally, the previous studies, most of the studies were collected samples and offline measurements. So this is one first time online measurements were done. So if we have more data sets, that will help improving our understanding and improve the parameterization. So in turn, we can better represent INPs in our cloud physics models. So this is a CFDC, continuous flow diffusion type chamber with a parallel plate design with vertical geometry. It's a semi-automatic instrument. It needs a lot of human interactions. Almost 8 hours a day is required to conduct a complete experiment, to pick it to different temperatures and all. So I will show some results. I'll skip this. Yeah. So one complete year, these experiments were conducted, and at these 3 temperatures. So one disadvantage is that still we could not go below minus 25 degrees Celsius. So we are working on how to go below this temperature. So what you see is the ice nucleating particle concentration increases with a decrease in temperature, and in different seasons you have different slight variations. So there are INP parametrizations already available in numerical models. Some are supersaturation dependent, some are temperature dependent, some are recently did temperature and aerosol concentration dependent. So we also try to look at our data put together to see how it varies with the temperature and how it varies with the coarse mode aerosol concentration. So we followed a similar to the Pandithurai methodology and try to look at how this INP concentration varies, and these, whatever you are seeing, some lines, dashed line is Meyer's existing parameterization, how it works. So as compared to DMART, our